Now I will try to solve all these three questions of the graph section. Then all the graph question of this playlist will be over. So for this question we have given an m cross n matrix. It is a binary matrix where 1 represent a land and 0 represent a voter. We have to return the number of islands. Basically, number of islands means a island is a land which is surrounded by the voter from all the direction. For example, if you see this one, it is surrounded by the voter from all the direction, and the direction that are possible here are 4 direction: up, right, left and bottom. We can't move diagonally here, it is not allowed. We can either move horizontally or vertically. Okay, so let's just define the size of our world. Let's call this grid our world. Int m is equal to grid dot length and for columns int n is equal to grid of 0 dot len gdh. Okay, so what we have to return here is number of distinct islands that are possible in our world. For example, in this case, these 4 lands are connected with each other via a up, down, bottom or right. And this is a separate island that is not connected to any other land. Basically, if you consider this as a component A, this as component B and this as component C, then you can clearly see that we can't go from A to B or B to C or vice versa, because there is no diagonal movement we can do in order to move from one land to another. We can only do a horizontal or a vertical movement. So let's just try to copy that example and let me try to explain how we will solve that question. Basically, 1 here is a land and 0 represent water. So for this example, you can clearly see that these are the 3 components that are there, because if we are at this land, we can go to here, here, then here, then here. And if we are at here, we can move to the other 3 places also. But if we are standing at this island, this component A, then we can't go to this component B. We can't go there because there is no diagonal movement allowed in this question. So clearly this is our component A that is connected within these networks, and this is our component B and this is our component C. Only these three components are possible here. So what we have to do is we have to return these distinct networks of islands, or basically we have to return the islands. So we have to return 3 in this case, because this is the one island, this is the second island and this is the third one. What we can do in this question is we can take the benefit of a graph traversal, a DFS or a BFS. Either one of is fine. Now if we try to do a DFS from, let's say, here, if we start our DFS from here, then this will get marked as visited. we can go to the left, it is allowed. Horizontally we can travel. Then we will move to this land, then this will be visited. Then we can move to the downward because that traversal is allowed. So this one will also get traversed, then this one will also get traversed. And once we reach this land, we can move up, but it is already visited. So we can't go there. And we can move to the down, but there is a water, so we can't move there. There is already a water body present, so we can't move to the down. Here also we can't move to the right because there is water. Here also we can't move to the bottom because there is water. Here also we can't move to the right because on the right side of this there is water, and on the left side of it this node is already visited, so we can't go there. So for this component, if we start our DFS traversal from this node, this source node, then all of these components land that are connected to it via the 4 direction will get visited as true. Then what we can do is we can stop our recursion and we do ans plus plus, signifying we have found all the land that are present in this component, and this is one island, so our ans will become 1, signifying this is the one island. Now in the if loop, if condition, what we can write is that if visited of some row or a column is still 0, then run a DFS loop again, and after that do our ans plus plus. So what here happens is, once this component get visited, our ans become 1, but still there is some land that have been unvisited. So now we move to this land and we again do our DFS. If we do our DFS, this node 1 will get visited. Here there is no land just besides it, there is no horizontal or a vertical movement here because it is surrounded by the water from everywhere. So our DFS will return, and our when our DFS will return, we will do ans plus plus, and this ans will become 2, signifying now 2 components are done. These 2 components are done. Similarly, again using this if condition, we will check are there any remaining ones left that are unmarked, that are not visited yet. So yes, it will output yes, these 2 are one of those. So when we found that one, we will start a DFS from there. We will start a DFS from here, and once we start a DFS from here, it will move to the up. See, it is a 0, so we don't have to include it. Go to the left, it is again 0, so we don't have to include it. It will get visited and it will check its right is a land, so it will move to here and it will make this also visited. And now if we check, we have reached all the one and marked all the ones as visited. All the lands are now visited, so there is no one left that are still unmarked, that are still not visited. So we don't do our DFS again and we will return our ANS. So I hope this is clear to you, all the approach here. Let me just quickly write the code so you can get a better understanding of it. So for this we need a visited array for the landmark. So let's just make a visited matrix. It will store that is that particular land is visited or not. If that is visited, then our work is done, but if that is not visited, we have to do a DFS because we haven't gone to that land yet. And if we haven't gone to that land yet, that means that is a part of a new component which we haven't visited till now. The size of the visited matrix will be same as the size of our world. Okay. Now what we have to do is we have to check whether our land is visited or not. If it is not visited, we will run our DFS. Otherwise, we will continue. So we will run our for loop for int I is equal to 0 to I less than m I plus plus, for int j is equal to 0 to j less than n j plus plus. Here we have to do our DFS. So we will do DFS. Sorry. First we have to check that is the component which we are currently at is already visited or not. So if we are at a land, so that means if grid of I comma j is equal 1, that means we are on a land, and our visited of that land is still 0, that means we haven't reached this land yet. So we will do a fresh DFS starting from a new component. We will do a new DFS here, and we will increase our ANS, signifying this is the one component that we haven't reached yet, but now after this DFS that component is reached. So let's just increase our ANS. At last I will return the ANS where I am storing our answer. Now I have to write the DFS logic. Clearly you can see there are the 4 directions where we can go: up, down, bottom, left or right. So let's just make that. Let's make a 2D array of direction. Zero comma minus 1. So these are our 4 directions, signifying right, bottom, left and up. So basically if you see this 1 comma 0, this 1 comma 0 means we will add 1 to our row and we will add 0 to our column. So basically column will remain same, but we will add 1 to our row. So let's say suppose we are at this position. If we do this row plus 1, then our row will get increased to this and our column will remain same. So this is kind of a downward movement that is going on using this 1 comma 0. Similarly, if you look for this 0 comma 1, let's suppose we are at here, and this 0 means we will add 0 to our row, and this 1 means we will add 1 to our column. So if we add 1 to our column, that means we will move to the right and our row is remaining the same. So we are on the same row. So it is kind of a right movement that is going on, that is captured by this array 0 comma 1. And similarly for this minus 1 comma 0, if we are at here, if we do row minus 1 and remain our column as it is, if we do row minus 1, we will move to the up, and as our column is remaining the same, so it is just a up movement. So this is capturing a up. Similarly this 0 comma minus 1, we are doing column minus 1, we will move to the left. So these are the all 4 movements that are possible in our setting. If they have told that we can also move to the diagonals, then what we can do is we can add another direction signifying 1 comma 1. This 1 comma 1 means we will add 1 to our row and 1 to our column. So let's suppose if we are at here, if we do row plus 1, we will go here, and if we do column plus 1, we will move here. So if we do both simultaneously, then we will reach this. This is kind of a diagonal movement here that that will be captured by this 1 comma 1, but it is not given in our question, so we don't need it. In our DFS, I will start our starting node, which our source node basically. Here, let's suppose if this is our source node, that then if we start our DFS from this one, it will capture all the possible ones where it can go. Similarly, if I start a DFS from here 0,0, then it will capture all the ones that it can travel. So all these one will be satisfied by the first iteration. Then this will be passed as a source node. It is the only node where it can move, so it will return the visited of this to be true, and we will run our for loop again using this. Then we will find this one as our source node, and this get marked visited via this source node. So we need a source node. So our source node can be captured by simply I and j, because I and j are capturing where we currently are. I signifying the row and j signifying the column. That is all we needed. So our source row will be I and our source column will be j, and let's just pass the direction array, and let's just also pass the visited array. Now all the things are passed. Let's just quickly make our DFS function. I hope you know how to do a DFS in a graph. Public void, as it is not returning anything, it will just update the visited array only, so we don't need to do a return anything. DFS, it will be a source row and source column. Then this is a direction array which will remain the same, so int direction array and our visited array. In a DFS algorithm, we just quickly make our source node to be visited. Here our visited of source is 0. Now we have moved to the DFS, that means we have processed that source node. So let's just make that source as visited, that source node as visited. What I mean by that, if we are checking this loop, it is saying that visited of I comma j is currently 0. That means it is not currently visited. But once we started our DFS, that means our this thing is now visited, this thing is now processed. So let's just make this visited true. So what we will do is we will make this true, visited of source row and source column is now visited. Now if this is visited, we can move to the 4 direction. We will check all the direction one by one. If we can go to there, we will move to that and do the DFS for the new row and column. But if that is out of the boundary, we will do nothing, and if that will be a voter that is there, we will not do anything. So for all the direction, because we can move to any direction, so let's just call a for loop for all direction. What will be our new column? New column will be direction of 1 plus our original column, that was source column, and our new row will be direction of 0 plus our original row. I have explained you why and how this new column and new rows are being processed via this example that I have told you, that if we will move to the down, that means our row will increase from original to +1. If this has a 1 in it, it will return 1 plus original row, so it will capture a downward movement, and similarly all the other direction also. So if our new row and new column are out of the bounds, let's suppose if we are at here and we are moving out of the bound, we move to the left, then we don't have to do anything. So let's just make a if condition that if we are out of the bound, we don't have to do anything. So we have to be in bound. So if our new column should be greater than equal to 0, because it can't be negative. Our new column that we calculated can't be negative. So new column should be greater than equal to 0. Similarly, our new row that we calculated should also be greater than equal to 0. Our new row should also be greater than equal to 0, because this is the 0th row. There is no minus 1th row. So our new row should also be greater than equal to 0. Similarly, our column, our new column should not be out of the bounds of this length of our column. Basically, total number of columns that are there in the world, that should not move to the out of the bounds. So our new column should be less than total number of columns. Total numbers of columns are n. And in the similar fashion, our row should also be less than total number of rows that are there in the world. So our new row should be less than total number of rows. Total number of rows are represented by this m. So this if condition will check are we on the correct bounds or not. If we are not at a correct bound, we will not run our DFS again. Now another condition that we have to check is, are we at a land or a water? If we are at a water, we don't have to continue because we can't move to the water. We can only traverse in a land. So we need to check that our new row and a new column has to be a land in order to move to that land. So if our grid of new row and new column is equal land, then we have to move forward. Also, one more thing, our new row and new column where we have to move should also be not visited yet. If that is already visited, then we don't have to redo all the for loop again and again. So I will write a if condition that if our visited of new row and new column should be equal to 0, that means it has not been visited yet. So now let's just go to this new row and new column and visit it. So we will do DFS of, this time our source row will become new row and our source column will become new column. Direction and visited will remain the same. Let's just submit the code and see is all the test cases are passing or not. So I haven't passed this m and n in the function here. So let's just pass that, our n and our m. Our n and m. Okay, I forget to pass the grid array also. That is the main array, so we need to pass that in our DFS function also. It's a char, so it will be a char matrix. Now it should get submitted. So all the test cases successfully passed, all the 50 test cases are passing, so our code is quite decent. As we know, it is a 2D matrix of n cross m, so our time complexity will be order of n into m, because we are moving and checking a for loop again and again, so it will be a n cross m time complexity, because there is a nested loop and we are moving from m, and in the nested loop we are moving to n. We are covering all the land, all the water bodies, so that's why it is a order of n into m time complexity. This is a simple DFS algo that I have written. In a DFS algo, we first visit our source node that we have processed it. Then I am checking all the direction that are possible, all the 4 direction that are possible here, and computing a new column and a new row. That is our candidate new source, and we will check our new source is in the bounds or not. If it is not in the bounds, we don't have to do anything, we will just continue. And if that is in the bound, then we will check 2 more conditions. The first condition is that our new source should be a land, that then only we will move to the land, because if it is a water, then we don't have to do anything, because we can only move or travel in a land, we can't move on the water. And that new row and a new column candidate new land should be not visited yet, because if it is already visited, then we don't have to do anything, we have already computed all the neighbors for that. Why we will do check that again and again if it is already visited? Let's suppose if this is already visited and we are at here, why will we move from this thing to the right? This is already visited, so we will move to the down. That's why I am writing this condition here. I hope all the conditions are clear, and how we are writing the code for this question is also clear. Now this is the second question of our graph section. This is a standard course schedule problem. Here the concept of Topological Sort will be used. For this question, there are total of number of courses you have to take, labeled from 0 to n minus 1. You are given an array prerequisites where prerequisites of a comma b indicates that you must take course b first if you want to take course a. So it's kind of a university setup where you need to take course b first, then only you can take course A. You can think of course B as a second level course and a course A as a prerequisite to the second level course B. For example, the pair 0, 1 indicates that to take course 0, you need to take this course 1 first, then only you can take this 0. So what we have to return is, we have to return true if we can finish all the courses, otherwise we have to return false. So why this question is a topological sort question? First of all, it's a topo sort question because there is some kind of a dependency going on between two nodes, A and B. You can only take A if you have already completed B. Topo sort is also explained via packages kind of system, that if you need a package B to do a work A, then you have to import package B, then only you can do A. You can't do like first do A then B. You have to do B, then only you can do A. Similarly here for the courses, you have to do B first, then only you can take A. And if you know a slight concepts of Toposort, Toposort basically what it does is it actually sort in order of the dependency, where the first elements of the Toposort are the first ones to be imported or the first one to be taken, and the last element of this Toposort will be dependent on the previous ones. So what I mean by this is actually is that, let's say this is a Toposort. No, let's say this is our setup, that you need to take course first in order to take this course 3, and in order to take this course 5 you need to take this course 3. Okay, and let's say this is also a condition there. I will explain you what each number here means. So let's say this is our graph. This is a graph given to us. We can construct this graph using an adjacency list or whatever, but let's see, that's not the point currently. So here what I mean by these arrows is, in order to take this course 3, you have to take this and this first, then only you can take this third. Otherwise you can't take this third. You can't do something like let's take 5, then let's take 6, then let's take 3. No, you can't do that, because 5 to 6 is okay, but you can't do 3, because in order to do this 5 you have to do this 3. So this is not a correct Toposort. So correct Toposort will be the first element that are independent of everyone. See here, the incoming nodes to this these vertices are 0. This is also 0. Incoming nodes to these vertices are 0. So these nodes are our independent ones. These ones are the courses that you need to take first. So what you can do is you can take 1 first, then 2, then 4, or you can also take 2 first, 4, then first. This order does not matter. Our Toposort will return the answer for sure. You can also do something like let's take 4 first, then 1, then 2. So either combination of these 3 numbers are fine, because there is no restriction in taking them. You can complete this second course first, then first course, then fourth course, or vice versa, because there is no conditioning restricting them. Now let's say we have taken this first, second and fourth courses. Now what else we can take? We can take this third course. We can't take the fifth course just after this taking of 1, 2 and 4, because if we take the fifth course, then fifth course is saying that I have an incoming edge from 3. I can only be taken if 3 is completed. Now the 3 course is not completed yet, so how you can take me? You can't take me. So what will be our exact Toposort's algorithm? It will say take 3 first, then only you can take 5. Similarly, now you can take 6. I hope this is clear, that this will be a one Toposort out of many possible Toposorting here. Okay, so the question is asking, we need to return true if all courses are taken. If all courses are taken. In this example, you can clearly see that we have taken this course, 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 without any issues, without any ambiguity or without any contradiction. So for this example, we will return true. And in order to like cheat this, what you can do is you can you know the number of courses, you know this number of courses. What you can do is you can store this toposort in an array or a stack, whatever, and you can check that if arr dot length is equal your n. If that is the case, we will return true, otherwise we will return false. I hope what I am saying is quite clear, that say if a toposort is giving n nodes, that means there is a possible toposort, there is a possible sequence of the courses you can take, so that no courses are in ambiguity. That means that n is equal to the arr of length, that means all the number of courses are taken. So if the toposort length is equal to your all the number of courses length, that means all the courses can be taken without any ambiguity. Where will the ambiguity arrive? Where will be the ambiguity arrive? Let's take a very simple case. Let's say there is a course 1, and in order to take course 2, you have to complete this first course. Then this is quite easy. You can take this as a toposort, one toposort, that you need to do first course, then second. This is a one possible toposort, and this is the only possible toposort for this currently. But now what I'm saying is there is a third course also that can only be done after the second. Then also this is a toposort, this is a valid toposort, and a student can do something like it can take the course first, then second, then third, and it will return this toposortic stack or whatever, wherever you are storing this. Let's call this a container. Now in order to take this course 1, what I will introduce is you can only take this course only if you have completed the third course. Now this is the ambiguity case. This is a contradiction, because if you do a dry run or simulate it, what it means actually is in order to take course 2, you have to be completed course 1. Okay, in order to go to class second, you need to complete the class first, and in order to go to the class third, you need to clear the class second. But what this cycle kind of structure is stating, in order to go class 1, you need to complete the class 3 first. This is a nonsensical thing. So this means there is a contradiction here. There is a contradiction. Here is your contradiction. And here we have to return false, because no matter how you will arrange the sequence of these three numbers 1 2 3 or 3 2 1 or anything, in all the cases the container will store a sequence that is not a toposort. For example, 1 2 3, what 1 2 3 means is in order to take course second, you need to complete the first. In order to take the third, you need to complete the second. But this is not the case. In order to take the first, you need to complete the third. So this third should be before the one. That is not the case. And similarly for all the other cases, you can find those things. So we have found two beautiful conditions, that if our stack length or a container length, which is storing the toposort, becomes equal to n, then we have to return false. Then we have to return true, signifying all the courses can be taken. Otherwise we have to return false. And if we detect a cycle, this is a cycle. If we detect a cycle, then also you have to return false. And these are the only three conditions that is there. We will do a standard DFS algo and we will construct our topo sort using a stack or whatever ways you are familiar, and we will check that in a DFS if there is a cycle we will return false, and after all the DFS, when our stack is filled, we will check that if our stack dot size is equal the total number of courses, that means there is a possible topological sort algorithm or a sequence containing all the courses. So you can take all the courses in those sequence, and that will not raise any contradictions. If our stack dot size is equal and basically our topo sort contains all the numbers, then we will return true, else we will return false. These are the three conditions, and we will only do a standard DFS algorithm calling. I have done a DFS in a previous question also, so I hope you know how to do a DFS, and I will show how to construct this toposortical stack also. It is very easy to do that, so that is not a problem. One approach before writing the code, what I can tell you, this is a DFS approach that I have shared you. Basically, in order to do a topo sort, there are two approaches, one with the DFS and one with the BFS. For the BFS approach, I will just show you the code and try to explain you that there, and for the DFS I will be writing the code. For the BFS also, the main algorithm remains same, that we will construct a topo sort and we will check these three conditions, that if there is a cycle we will return false, otherwise if that n is equal to the stack dot size, or in a BFS approach we apply a Khan's algorithm, if I know, or a Kruskal, I don't know the exact name of the algorithm, but there is that. Let's just see that and try to write the code for this question. So let's just first try to see my solution for the BFS part. So this is a DFS approach that I have written, so let's just ignore this. So this is also a BFS. Maybe I have solved this question using BFS only, but you can check how to do that using a BFS approach also. It is quite easy. Maybe this thing. This is also a BFS approach if I'm not wrong. Okay, so never mind, let's just ignore this. Okay. So first of all we will construct our adjacency list. We will construct this graph. And how we will construct this graph? Let's say what is given to us. The given to us is such that the prerequisites of 1, 0 means we need to take the course. To take course 1, you need to take course 0 first. So this, if we have given 1, 0 like this, that means in our adjacency list the graph will be something like this, that in order to take this first you need to take this 0. So in order to take this first you need to take this 0 first. So that's how our adjacency list will be filled. So let's just make adjacency list first. Array list of integer, let's call this ADG is equal to new array list. and there are 0 to n minus 1 courses. That means there are n courses because of the 0th indexes. Let's just call this n only. So we will fill our adjacency list with the empty array list first. For int I is equal to 0 to I less than n I plus plus adj dot add new array list. So this is done. Now we will fill our adjacency list with this same logic. Let me just show you how we will do this. Let's call this edges. So for int one edge in this edges, we are looping through all the edges. So we will extract this one edge is like 1 0, and we will do adj dot get e of 1 dot add e of 0. So you can think of this e, a single edge, as 1 0 1 0. What I am doing is I am assigning adj dot get e of 1, this 0th e of 1, because this is the 0th index, this is the 1th index. I am getting this 0th index and adding 1 in it, I am doing something like adj dot get 0 and add 1 to there and 1 to there. Now in any other edge, let's say in any other edge something like 2 0 occurs, then also what happens is I will get this 0, and add 2 there. So our new adjacency list will be something like this. That means in order to take 1 and 2, you have to take 0 first. I hope this is now clear. So this is a singular edge. This is a directed graph which we are building, so there is no need to add the vice versa of this. That is for the undirected graphs, and it is very trivial. Basically it is very trivial that we are finding a toposort, so there has to be some kind of arrows or some kind of a direction. If that is undirected, then we can't even find a toposort, because for the toposort we need a directed acyclic graph, with no cycles. So you know what we are doing is we are finding a toposort and we are checking is there a cycle involved in anywhere. Okay. Now as for the toposort, we need a stack, so let's just build the stack of integer. Let's call this st is equal to new stack of, we don't need to specify that. So at last what we will do is that if after the DFS or everything, we will check that if stack dot size is equal n. If that is the case, we will return true, otherwise we will return false. And now the only thing left is the traversal thing and building a toposort and finding is there any cycle involvement during our DFS or not. If there is any cycle detection, we will again return false, signifying we can't access all the number of courses in a toposortical manner, because everything is dependent on each other and there is no clear thing like a linear path going on where we can start with A, then B, then go to C or something like that. So let's just initialize our DFS, and while doing our DFS we need to also check our cycle, is there any cycle involvement in there or not. So for the DFS we need a visited array, and for the cycle detection we need a current visited array. So let's just quickly make those two, that int visited is equal to new int of n, and int current visited is equal to, again size will be the same. I hope you know how to do a detect a cycle in while doing a DFS. I will also explain that broadly. Now we just need to do our DFS, and in our DFS what we will call our adjacency list. We will pass our stack. This will store our topo sorting order. We will also need to pass our visited array and our current array. And for the DFS what we needed is for the DFS we need a starting point, a source node. The start of topo sort will be our node. Let's call this I, and we will run a for loop checking all the nodes, starting from all the nodes. If that is already visited, we will continue. If that is not visited, we will pass in our DFS. This is simple DFS traversal I did in number of component question, the previous question. 0 till I less than n, I plus plus. If your visited of I is equal 0, that means it is not visited yet, then only do the DFS. Now let's just quickly define our DFS, and while doing the DFS we are also checking is there any cycle involvement or not. Let's suppose if there is a cycle involvement, if cycle is equal true, we need to return false. So what our DFS function will return is, our DFS function will return whether the cycle is present or not. So let's say public boolean DFS. Let me just quickly write the parameters. First it is adjacency list, so let me just copy this. Then it's stack where our topo sort will be stored. Where is the stack? Yep. And then there is visited array, and then there is current visited array. So let me just quickly pass these two also. Visited array and currently visited array. And lastly I will pass the node, the current node. So let's just call it int u. Now why this is boolean here? Earlier in the num components where we have to return the number of distinct components or the distinct island, there it was void because we were just doing a traversal DFS. But here we are doing traversal also, and side by side we are trying to find is there any cycle involvement or not, because we need to check whether there is some kind of a cycle or not while doing the DFS. While doing the DFS we are checking is there a cycle or not. If we detect a cycle, we have to return false. If there is a cycle present, we have to return false. So if this boolean is cycle, so if cycle becomes true, that means while doing the DFS of this I got a true answer, then I have to return false. So if your is cycle is equal true, we need to do what? We need to return false. Whenever there is cycle present, I got an answer as is cycle true, and if there is cycle present, I have to return false. That's why I am returning false as an answer. That no possible combination of Toposort is possible there, which a student can take in order to get all of the courses in a topological sorted manner. That means everything is dependent on each other in some kind of way, and there is cycle involvement. Okay, let me just quickly write this DFS code now. Firstly, we will, in the DFS, we are passing the node U, which is not currently visited. So let's just visit that. So visited of visited of U will be 1, and current visited of U will also be 1. This is simple DFS which I am doing here. Then we go to the neighbors of the U. So for int v of adjacency list, because how we get the neighbors of U? By using the adjacency list dot get neighbors of U, and I am calling the neighbors of U as variable v. Now we need to check two things, because we are side by side checking whether there is cycle involvement or not. So let's say if your visited of v is equal 0, it means it has not been visited yet. Then simply we have to simply visit it. So we will just simply return, let me just think here, we need to do a traversal here. We need to call the DFS for vth now. Okay, so let's just call that DFS of adjacency list, comma stack, comma visited array, then current visited array, and then this time we will call v. And if this return true, that means there is cycle in the next traversal. Then also we have to return false. So if this returns true, then what we have to do is we have to return false. And if while doing all the DFS none of the path says there is cycle present, then okay, sorry, my bad. Here the DFS of this is saying there is cycle there. This DFS of adjacency list of v is saying when I did the traversal for the vth neighbor, I found a cycle because it is returning true. So if it found the cycle, that means for the DFS of u also there is cycle, so we have to return true here. That means it is basically saying that this line is basically saying that for the vth node I found a cycle in it. I found the cycle in vth node when I did the DFS. So now what you will say? You will say that my neighbor v has found a cycle. So I have also found a cycle, because cycle is universal to all the nodes here. If one node finds the cycle, that means the above node also contains that cycle. So it is saying like my neighbor v find a cycle. So now I have to also return true. That means there is a cycle present in me also. That's why we are returning true here. And at last we will return false, signifying no, we don't find any cycle. If this return true statement did not run, that if this did not run, that means If this does not run, that means this statement is not running. So we don't find any cycle. In that case, u is saying basically all the neighbors of u are saying we don't find any cycle. We don't find any case where return true was true, that the cycle is present. We don't find any case. So you will also say that my sub neighbors, my neighbors did not find any cycle. My all neighbors did not find any cycle. So I also did not find any cycle. Okay. Now the only thing left here is to check the cycle, that is there a cycle present or not. And in order to do that, it is the only case when visited is 1 and current visited of v is also 1. That means in the path where we are going, v is already visited, the neighbors is already visited, and this is visited via going from this path again. That is the issue. That means we have found a cycle. Let me explain you that in detail for a moment. Okay. So let's say we found a cycle, something like this. Okay. Here, this is u, and it will go to the v and check. Now this 2 is visited, now this 1 is visited, and in the current path it is visited. So current of visited of these will also be 1, and then this will go, we will go to this 3. Now all the visited of 3, 1 and 2 is 1, and also current visited of 1, 2 and 3 is also 1. Now when we do this, we go to this, we see that visited of 3 is 1, and also current visited of 1 is also 1. That means in the traversal which is currently going on, this is the current traversal which was going on, there visited of 1 is also true, and current visited of 1 is also true. That means this node is visited, and this node is visited when I am doing current visit. Because let's say a 4 is here and it is visited, but it is not in the cycle. So for this, visited of 4 will be true, but current visited of 4 will be 0. In this case, there is no issue because it is not a component of the current traversal. The problem of the cycle arrives when there is the traversal going on, and in that traversal you found that while the traversal is going on, while the current traversal is going on, and you find out that somehow the next element, that is v, is already visited. In the current visited of that is also 1. That is the problem where we have found a cycle. So let's just do that. Let's just write that condition. The condition is simply, I have explained you that if visited of v is equal 1, that means it is visited, and it is visited in the current traversal that is going on, then is the issue. Because let's say in some other component which is not at all connected to these guys, that is visited. Let's suppose we have visited that. Now for that node the work is done. That is not saying that the cycle is present or not. That's why we need to check the current traversal node also. Current visited of v is also 1. Then only we have found a cycle. So we will return true. And at last, after the current traversal, we will keep the visited of v as 1, but we will change current visited of u as 0. That means this, for u the current traversal is done. Now make the current traversal of u back to 0. because its work is done. Current visited of u is 0. See, this visited is checking the state for all the nodes, whether they are visited or not, globally across all the nodes. So if anytime it becomes visited, it will remain visited. That means we have gone to it one time. But this current visited is storing the current path, the current DFS which is going on, whether that u node is visited or not in the current path. So in the forward phase, we will set that u is visited and we will check the current paths of u. Then when in the backward phase, when the function returns back to u, we will make current visited u back to 0, signifying this is not part of any path that is currently visited going on. Now I hope this is completely clear to you. Let me just run this and check. Okay, so some issue is there currently. Let me just see that. Let's do this, like boolean is cycle. If there is cycle for v, we will return true. That if is cycle, that means there is cycle present, we will return true. Otherwise we will return false. Oh sorry, I'm not filling the stack because we need to find the topo sort also side by side. So with this I will add our u to our topo sort, and where we are storing our topo sort, we are storing topo sort in the stack. This st.add or push, whatever the command will be, we will figure out. We will add that u there, signifying we have found one topo sort for that. So all the test cases passed. I hope the algorithm is completely clear to you. I have explained it multiple times, again and again, same things. Let's just move on to the next question. This is the rotting oranges question. This is again a classical question, and so many doubts regarding this will also get clear in this last question of this graph section. So what we have given is, we have given a grid here where 0 represent an empty cell, 1 represent a fresh orange, and 2 represent an rotten orange. So m cross n grid is there, so let's just initialize the lengths of these. So int m is equal to grid dot length, and our int n is equal to grid of 0 dot length. I don't think I have to explain this, how we are getting this m and n. Basically this m are number of rows and this n is number of columns. Now here 0 represent an empty cell, 1 represent a fresh orange, and 2 represent a rotten orange. Every minute any fresh orange, that is 4 directionally adjacent. Now similarly as in the number of island problem, we can go to the 4 direction that are left, right, up and down. Here also we can go to the 4 direction, up, left, down and right. So let's just quickly make that array for the direction array, which will signify how we are traversing. I have already explained you in the first question of this graph that how that direction array works internally. So for now I will just initialize that direction array 1, 0 for the downward motion, -1, 0 for the upward motion, 0, 1 for the right motion, and 0, -1 for the left motion. So this is completely clear now. Okay. Now till now we have done the DFS only for the first number of island, and for the course schedule I believe I have only done the DFS. But for this question we need the BFS because we will search in the breadth first order. That means we need to search one by one. We need to search level by level. Every minute any fresh orange that is 4 directionally adjacent to the rotten orange becomes rotten. Return minimum number of minutes that must elapse until no cell has fresh orange. If this is impossible, return -1. So what we have to return, let me just quickly explain that what the question is asking. The question is saying we will be given a grid, we will be given a grid of some kind, and in this grid some are rotten oranges, some are empty spaces, and some are the fresh oranges present. And what this question is stating that 0 is represented as an empty cell, 1 is represented as a fresh orange, and 2 is represented as a rotten orange. So let's suppose if there is 2 here, 1 here, 0 here, that means this is a rotten orange present here, here is the fresh orange, and here is the empty cell. So let's suppose if here the zeros are present, that means these all are the empty cell, here is the rotten orange, and here is the fresh orange that is present. Okay, and the question is saying that in every minute that passes, a fresh orange that is adjacent to this rotten orange will also get rotten. So this after 1 minute of unit, let's say unit, because we will not actually simulate the 1 minute here, we will use kind of a 1 minute as a unit, we will consider it as a unit. In physics I hope you know how this unit, why I am saying this unit. Okay, so whenever that unit passes, whenever that thing passes, 1 unit passes or 1 minute passes, the adjacent to the rotten one will become rotten also. Now let's suppose this is our initial configuration, and that this basically means, let me just use this pencil for the rotten oranges. This is the rotten orange 1 and this is the rotten orange 2, and all the other ones are fresh oranges. All the other ones are the fresh oranges that are present, and zeros are the empty spaces. That means there is nothing present there. So let's suppose after 1 unit of time, what will happen? After 1 unit of time, what will happen is, let me try to simulate in this grid only. The condition is after each minute, the rotten orange will rot adjacent fresh oranges. So when 1 minute passes, this rotten orange, first we will look into one rotten orange, this rotten orange will rot this adjacent orange, fresh orange, because one was the fresh orange. It can't rot this 0 because it is empty space. It can't rot this 0 because it is empty space. And it can't rot this 1 till now because it is not upward, downward, right or left connected to this rotten orange. Now simultaneously, please focus on this word, simultaneously, this too will say I will also rot the fresh oranges that are directly adjacent to me. So in the first iteration only it will rot this one and it will become 2. Now in the second iteration, what happens? In the second unit of time, this is the new rotten orange that is present. Now this will say whoever is the fresh orange near to me, in the next unit of time I will make that not fresh. So now this will say, because of me, in the next unit of time, till now 1 unit of time is passed. In the 1 unit of time this become not fresh and this become not fresh. Now in the second unit of time, this will say make this as rotten. Now what about this? This can't rot any fresh orange because there is no fresh orange connected to it directly via 4 direction, not present. So it can't do anything. Now this is the new one. So now the 2th iteration is also done. But now this new rotten orange is in our basket. Now this will say, in the next minute I will make this not fresh. Similarly, this will say in the next minute I will make this new fresh orange as a rotten one. So it will go like 3, 4. And now if we keep on simulating it, keep running it, there is no way that this one become rotted, because there is no rotten orange directly connected to it. So there is no way to reach here. So what we have to at last return, we have to return -1 if there is impossible to make all oranges rotten. So what we will do is, we will traverse in this grid, and check each box, that if each box is 2 or 0. If that is the case, we will continue. That means that is good. But if we found that any box is still 1, that means if there is any box that is still present after the traversal, there is still a orange that is fresh, then we will return -1. Otherwise we will return the time. Here the time was 4 unit of time. If somehow this one becomes rotted, then we will return this 4, the time which it took to make all the oranges not fresh. So I hope the ending condition is quite clear to you, that in the ending condition, after the BFS traversal, we will run a for loop in our grid, and we will check that if anywhere there is fresh orange still exists, we will return -1. Otherwise we have to return the BFS. Otherwise we have to return the level. Okay, or the time which it took to make all the oranges rotten. Now what will be our initial configurations? This is the ending part which I explained you here. This is the end part, that we will run our for loop and check this condition, that if anywhere If anywhere our box becomes 1, we will return -1. Otherwise we will return levels or the time which it took to make all the oranges rotten. Now what will be our initial configuration? Initial configuration, if you remember what I did, I found all the rotten oranges that are rotten. I found all the part of those location and started traversing in them simultaneously, because if you remember at the start this was 2 and this was 2, all the else was either 1 or 0, all the other columns were either 1 or 0, only this one was 2 rotated orange and this one was the rotated orange. And what I did then was, for the first iteration, for the first minute of time, I simultaneously traverse in both of these. I go to this and I simultaneously go to this. After 1 minute these two becomes rotten, and after the 2 minute this become rotten. If you see clearly, what happens is I am taking all the oranges that are rotten, So what is the starting point of our traversal? Starting point of traversal is the point where our grid of I comma j is 2. That means if this is the point where a rotten orange is present, then only after 1 minute it will make other fresh oranges rotten that are adjacent to it. That is quite common sense. So we have found our starting point. So this is our starting point. So our starting point, well, basically our source node will be this I comma j, signified by this I comma j. So wherever we found that this is the box where rotten orange is present, we will store that in our queue data structure. Add that there, add that there, add that there. And if you see clearly, we need I comma j to signify that node. So for the queue, what will be the data type? For the queue, data type has to be pair. The first one will store the ith, the row which is where the node is present, and the second one will store the column in which that node is present, or either the pair, or we can say int, basically array of length 2, where the array of 0 will represent the row and array of 1 will represent the column. And we will add all those places where the rotten orange is present. That means if rotten orange is present, we will add q.add I comma j. Now in our queue, all the rotten oranges places are there. Now we will do our BFS there, and while doing the BFS, this will become 2, then this will become 2, and whenever that become 2, what we will do? Whenever that becomes 2, we will do what? We will add that in our queue. This is the standard BFS. I hope you know how to do a standard BFS. I will write the code for that also. Sorry, my writing is bad currently because I am quickly explaining this question as I have to go somewhere, and that's why my writing is like this. But I have explained the crux of this question clearly, I believe. Now algo is quite clear. Let me just write the algo clearly. So let me just write it in pseudocode. So what we have to do is, we have made our direction array, done. We have to make our visited array, we will make that. Okay, now we have our grid. We will check all the source node. We will check all the roten oranges location, all the source node, all the roten oranges location, orange location. And to check that, what we will do is we will run our for loop from I equals 0 to n, then our for loop, nested for loop from j to n, and if our grid of I comma j is equal to, we will make a queue data structure of pair or integer, and we will add this I comma j in that queue dot add I comma j, signifying now the initial run is done. And while doing this, we will make the visited of this also equal to 1. This is quite trivial, that means this is already visited, so we will also do the visited of this as 1, visited of I comma j as equal to 1. That means this is visited. This is very trivial. Okay, now the initialization is done. Now we have to do the BFS, our actual BFS. We have to do the actual BFS. And if you know, in the BFS, what is our condition? We will run our while loop, and while our queue is not empty, we will do our BFS and we will take all the present nodes, because we have to do the simultaneously stuff. So we will do a BFS here. Let's say we will do our BFS here, and at last what we have to check is, and here what we can do is we can also maintain a, here we can also do when our BFS will stop, when queue becomes empty. Yep, so that's good, I believe. Whenever the queue becomes empty, our BFS will stop. So we will maintain a ANS also. We will maintain an ANS also. That will control the time, because at last we have to return the time where all the oranges become rotten. So we will store that time also. We will do the BFS here. We will do the BFS. I will write this BFS logic in the code itself, but I hope the BFS is quite clear to you guys. And at last, what will be the last condition? Last condition, we will again run a for loop. We will again run a for loop from I to our m, then our j to our n, to access all the rows and columns. And we will check that if grid of I comma j, after all the BFS, there is still one fresh orange present. If there is one fresh orange present after the DFS also, then we will return -1, because that was asked in the question, that if after the DFS, or it is impossible to make all the oranges rotten, then we have to return -1. So we will return -1, otherwise we will return our ANS. And this ANS, how we will get this ANS? We will get this ANS via this BFS. Because in BFS, what we do? We do level order searching. This will be the first. Let me just quickly give you the abstraction of this also. Let's suppose this is a rotten orange present in the basket, and here is the rotten orange present in the basket. And if you know BFS search like this. Okay, now after this will be completely clear to you. Let me just start from the very basic. Okay, so the DFS, let's suppose here are the nodes. These are all the fresh oranges, and all the black spaces are empty spaces. Okay, so if we do a if we do a DFS, let's suppose if we are doing a DFS and this is our source node, what happens? First this get visited, then 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 this get visited, and then this get visited, then this get visited, then this get visited. Basically, we are this by the DFS we are committing to one branch, and when that branch gets completely visited, then only we are going to the next branch. This is our DFS logic. Go to the depth of one branch first, visit those branches first, then return. That is the DFS for you. I was just checking the recording is still going on or not. Now let me just simulate the BFS for you guys. And the BFS states that first go to the one level. One level will be this, and this will mean 1 minute. This will be the 1 minute. One level. All the one edges, the one level edges, or the edges that are just one edge away, all the nodes that are one edge away from the source node get visited. Now in the second minute, these will get visited. The second one will get visited. And in the third iteration, the remaining one will get visited. This is the BFS logic. And if you see that, let's suppose this is our source node and this is our rotten orange. This is our rotten oranges. And these are all what? These are our fresh oranges. Whenever we do a BFS, it is like of a filling of a cup. I know this is sound ridiculous, but think of it like a map kind of data structure. What happens when we do this? This will go to all the levels. This will simultaneously go to all the first level. This will go to the simultaneously all the first level on the first minute. This will go to like this. All the paths that are possible in the one direction. Then for the second minute, these will go to the next one. These will go to the next one. These will go to the next one. And for the second one, this will go to the second one. This will go to the second one. As this was the first, now this will, for the second minute, this will go to the second level. This will go to the second level. And this will go to the second level. And for the third distance will go to their appropriate nodes, like this. A BFS goes like this. First level, then your second level. I hope this is now completely clear how this rotting effect is going on. This was our rotten orange. In the first minute, it makes these oranges rotten. Then on the second level, these rotten oranges make these other fresh oranges rotten. That's how this BFS is going on, and why we are using a BFS. Why? Because we need these levels. We need these levels and these levels. I hope this now you get what this level means. This is a source node. This is the node. This is the first level of the BFS. This is the second level of the BFS. So firstly, this rotten orange will make this fresh orange rotten, then this rotten on the next iteration, on the next minute, will make this fresh orange rotten. I hope now this is completely clear. Now just I have to write the code only. We need queue, so let's just make that. As I have said, we need a pair in it, or we can use a array of length too. And in Java, how we define a queue, how we initialize that, we use linked list, an inbuilt class of this. Now the initial step I have explained you. Initially we have to find all the rotten oranges. We have to find all the rotten oranges in the grid. So we will find all the rotten oranges in the grid. For int I. Okay, so I have to make a visited array also. As I have explained you, we need a visited array. Maybe our work, let's just make a visited array. Because we are just making something extra only. We are not making something less. If we need that visited array, we will use that, otherwise we will ignore that. It is good to do more, but it is bad to do the less. So let's just do the more only. If we needed that, we will use that. That's the concept. Int I is equal to 0 to I less than m I plus plus. Now the nested loop for the column part. If grid of I comma j is equal to, we have found a rotten orange, we have to add that in our queue. So we will add that to our queue. Queue dot add new int in our queue, and our first position will store the row and the second will store the column. So first will store the I and the second will store the j. I have already explained you this. Our first position will store the I and the second position will store the column. So this is simply ARR of 0 and this is ARR of 1. This is a syntax only. You can simplify that if you are confused here. And here also we have to make a visited of I comma j also 1, signifying this rotten one is already visited. We don't have to visit that again, because a rotten orange will not become rotten again. That is already rotten. So we don't need to visit that there again. So visited of I comma j will also become 1. Now the initial part is done, I believe. Initial part is done. Now the queue will store all the source nodes, all the rotten oranges are there in the queue itself. Now we will do our BFS. And for the BFS, we write the condition while our queue is not empty. Okay, let's just do the BFS part differently. I have to make a answer also, int ans, where the timer will be stored, and this is what the question is asking, so we will return that. This is a timer where all the oranges become rotten. Now let's write the end part first, and the end part I have also already explained you what is the end part, where I have written the code for that. I believe this is the code for the end one, that if we found any box where still a fresh orange is present, we will return -1. For let's just copy this, because this is the traversal only I'm doing. Let's just remove this first. Okay, so this is the for loop accessing all the rows and columns. Now for the end part, what I have said that if anywhere we found that box, if in a box we have found a fresh orange, that means we have to return -1. That if grid of I comma j, I believe I have written the algorithm for that also, where it goes. Yeah, so here it is. We go from I to m and j to n, and if we found that in our grid there is still a fresh orange present, we will return -1. Found a fresh orange, we will return minus 1. Else we will return our answer only, and this answer will come from the BFS what we did here. So this is the BFS, and I have explained how the BFS logic works, how the level works. So whenever one level will be completed, we will do ANS++. And to simulate one level, we need to access all the nodes, we need to access all the source node, because we are doing this simultaneously. We are doing, let's suppose this is S1, this is S2, we need S1 and S2 both, then only we are doing the second traversal. So for this, all the source nodes are present in the queue itself. So let's just find the size of the queue. Size of the queue is queue dot size. Now we will write a for loop for int sources in our queue let's just call this I only. Okay, now you will get a better understanding that int of source location, what is the location of the source? We will get that from the queue itself, because queue contains the sources, no? Because we have added the sources in the queue, and here we are extracting those sources. So we will get that queue dot poll. This is the statement you write to remove and get an element from a queue. And source row is equal to, what is the source row? I have explained you, in the queue the first element is storing the row. So source locations 0th, and source column is stored in the source location first index. By writing this for loop, we will get all the source location, because we are removing all the nodes that are present in the queue. We are removing all the source nodes that are present in the queue one by one, and getting their location and storing them in these variables. Now we have to do our traversal. We will check the direction. We will check the direction up, down, right and bottom, and check if they are in the bound and the visited of them is still 0. We will visit them or something like that. Let's just see that. Now we will check for all the direction. This is the same logic I have done in the first question, that for direction in directions, for int directions in directions, our new row will be original row plus left, right, or whatever there is stored in this direction array. And new column will be original column plus direction of column part in the direction. This is the same logic I have explained in the first in more depth, that how this new row and new column is getting calculated using this direction array. Now we need to check the bounds. That let's suppose if we are at here, let's suppose we are at this source node and we go up, we can't go up. So we need to check this, is this new row in the correct bounds or not? What are the correct bounds for the new row? The correct bounds for the rows are, it should be from 0 to m. It should be 0 to m. If it is m plus 1, then also it is wrong. If it is less than 0, then also it is wrong. So let's just do that. If our new row is greater than equal to 0, then it is good, and it should be less than number of rows there are m rows, and if the new row calculation give m plus 1, that is wrong. That is out of the bound. So we need to search only in the inbound. So that will be n underscore r less than m. And for the column also the same condition will be true, that it should be greater than equal to 0 and it should be less than number of columns present. So new column should be greater than equal to 0, and new column should be less than total number of columns. Total number of columns are n. So do that. Okay. Now we have got that we are inbound. We are searching in an appropriate area. Now we have to check whether it is an empty space or not. If it is an empty space, we need to continue, and if it is fresh orange, then only we have to do our traversal, because we can't do traversal in an empty space, as I have explained you in the earlier. That, see, between these fresh orange and this rotten orange, a zeroth location or an empty space is there, so we can't directly hop from this. So actually we can't visit this empty space. We can only visit if there is fresh orange present in that location. So let's just do that if our grid of I comma j is equal 1, then only we have to do our traversal. Sorry, I comma j means new row and new column. So now this we have to make it row-turn, and in order to make it row-turn, what we did? We set it to 2, grid of n underscore r, n underscore c. We will make it row-turn, and for the row-turn oranges, what we are doing is we are making them visited and we are adding them in the queue. Because let's suppose here the grid of I comma j was 2. If we found our rotten orange, what we did, we add them into the queue for the next level passing, and we make them visited. Similarly, we have found that this is the one which we have to make a rotten orange now. So let's just do that. So we will add new int, this new row and new column, signifying this is the new rotten oranges location that is just become a rotten one. So we need to process, or we need to travel for this rotten orange also, by making this source, then traveling again. New column, and we will make it visited of I comma j is equal to 1. Why I keep on writing I comma j? It's n underscore r and n underscore c. And similarly, when our one pass is done, we will make ans plus plus, signifying 1 minute is over. And 1 minute is over when all the source nodes that are rotten gets extracted from the queue and gets processed. See, this for loop basically outside this for loop. See, this for loop is extracting this for loop is processing all the source node that are rotten for this level, for the 0th minute, let's say. And whenever all the starting source rotten oranges are processed, we will go to the next part, we will go to the next iteration. So we will do ans plus plus, and we will again do this for the next ones that got added in the queue via this statement. Let's just run this and check, is there any issues in our code? But I believe we have written all the code by checking the exact issues why this is failing. Okay, so some issues are occurring. Yeah, so here we need to check that is that already visited, that if that is already visited, then we don't have to go there, na. So here we need to check that is that thing visited or not. If that is not visited, then only we will visit that. That's why I was maintaining this visited array, because if let's say I did not write this visited array, then also it may have run, but here I found a bug in my code that we need the visited array for this code. So this statement, what this condition is saying, this condition is saying that we are in the bound, we are in the correct bound, so we can proceed to calculate our new source that will be there. And what are the conditions for the new source? The new source conditions are that it should be fresh, so the orange should be fresh, then only we will make this orange rotten one, and that should be not visited till now. If that is already visited, that means some other rotten orange already covered that, so we don't need to cover that again. Now I believe all the test cases should pass. Still some issues occurring. Okay, so some bug is still coming. Okay, let me just quickly try run this. All the directions are correctly made. Passing that in the queue. What is the issue coming? We are outputting 5 and the answer was expecting 4. So we are doing one extra minute. So here is some issue. On the updating of our level is the issue occurring. Okay, so now I get the part why this is happening. Okay. See, what is the condition on updating a minute? On updating a minute, basically this ans++, the condition is such that if there is a fresh orange present directly adjacent to our rotten orange, then during that minute that rotten orange will make that fresh orange a rotten one, and then we are doing a minute one plus plus. Okay, that is correct. Now what about, let's say all the oranges become rotten, then only we are, then again we are doing this for loop for that. What I mean by that is that, let's suppose in our queue in our queue in our queue in our queue, let's suppose there is still a orange present, that is a rotten one, or by directly adjacent to those are rotten ones only, or the empty spaces are there, and if we do the traversal for that, then we are not actually finding any fresh orange to do the next minute, but still we are updating our ans++. So what we need to do is we need to make a flag checker here. Let's suppose a boolean checker. Let's initialize it to false first, it will say that it will check that is change occurred in this iteration or not. So again I will explain you this, that let's suppose what is the condition of doing this minute plus 1. We are doing this when we found a fresh orange directly adjacent to the rotten orange, and during that minute we will update that fresh orange to a rotten one, then only a minute will move. Okay, so this boolean checker will check that is there any change occurred or not. Change means from a fresh to rotten one occurred or not. If that occurred, then we will change our minute, otherwise we will not change our minute. That means if our change happens, here is the change happening. So if our change becomes true, that means change happened, a fresh orange changed to a rotten one, then we will update our minute. Otherwise we will not change our minute, because let's suppose in our iteration we did the whole iteration. Let's suppose take the very trivial case only. It is a very trivial case. Now you will get the whole understanding why this check condition is there. Let's suppose there is no rotten orange present in the grid. If there is no rotten orange present in the list, then our queue will be what? Let me just reiterate that. Let me just show you that here. Let's suppose this is our grid and this is 0 and this is 2. Okay, this is the case where if I did not write that change condition, our initial code was failing. Let's suppose this is our grid. Initial step is finding the source node. This is our source node, so we will store it and we will add this in our queue. So now queue is not empty. Because there is something present in this queue. So we will run this. Now our S will be 1, so this for condition will also run. This will run, and we will not find any case where this thing happened, that our fresh orange changes to a rotten one. We did not find that case, because by the definition of this grid there is no one present only to make that rotten one. But see here, after doing this for loop, in that case also we were doing ANS++. After that. So we will do ANS++ and we will return the answer for this as 1. But what is the correct answer for this? The correct answer of this is 0, because there is no fresh orange present in it altogether. So how we are returning a 1? Because 1 means after 1 minute every fresh orange becomes a rotten one. But there is no fresh orange present only, so how we are returning this one? This one is wrong. We have to return this 0. So that's why we need to maintain a checker boolean which check is any change occurred or not. That if there no change occurred at all, then there is no need to update this answer. For these cases we are maintaining that boolean. I have explained you why our code was failing and why this change is needed. I have dry run this, that if you take 0, 2, this as source node, then also we are doing ANS++, so we will return 1. This 1 basically means we did a 1 level traversal. After 1 minute all the fresh oranges become rotten, which is correct, but in the 0th minute also all the fresh oranges were rotten, because there was no fresh orange in the first place of the grid itself. So we need to return the 0th answer. So now this should work, I believe. Let's hope for the best. Yep, so all test cases passed, all the 300 test cases passed. And what will be the time complexity of this? Time complexity of this will be m cross n, or O of m cross n, because we are doing a nested loop kind of thing here, m and n. Here also we are doing that, so it will be 2m cross n. And for the BFS, in the worst case it is still m cross n only for the matrix kind of structure, for the grid kind of structure. So actually we are doing order of 3m cross n, that will come out to be m cross n only. I hope you know the time complexity, how that works. And for the space complexity, we are maintaining a visited array, so that will be m cross n again, because in this queue, in the worst case also, we will add all the rotten oranges here, so that will also be m cross n only. So our space complexity will also be m into n, and our time complexity will also be m into n. So now our all the graph questions are done. In the next one, I will try to solve the hash maps one. Where are the hash maps? These, all the hashing ones or the heap ones, I will try to do that.